Welcome to today's AVA session. My name is Snigdha Sarkar, and I am the CFD Application Engineer here at KETIV Technologies. Today, we're going to be having an AVA focused on the structure side of things. It's going to be hosted by a structures application engineer, John Dow. Our topic today is rapidly engineering and analyzing multiple designs using DesignXplorer and Ansys Mechanical. And with that, I'll let JD take it away.
Yes, hi everybody. Good morning, and thank you for joining me for this AVA session, which stands for the Ansys Virtual Academy. Feel free to join or subscribe to our virtual academies because there's also an Autodesk one. So for this AVA session, we're going to be continuing from my last one where we introduced parameters. For the agenda today, we're going to go over a problem statement. And then we're going to set up parameters for the model itself. And then we're going to jump into using DesignXplorer to do response surface optimization. And that's a workflow going through setting up a design of experiments, understanding the responses, and choosing how to optimize it and what we want out of it. So jumping into the problem statement. Let's say for this story, we designed a bracket that's supposed to be supporting some type of instrumentation, and it needs to take a 2,000-pound load, and it's fixed at these points against a wall. And it's important because it's holding an instrumentation device, and it's supposed to take measurements. And this device, let's say it just weighs 2,000 pounds. And we discover that after mass producing these brackets, we didn't do a simulation. We thought it'd be fine. And we might have messed up our hand calculations initially designing this. And we discovered that it deflects a little too much. The deflection is supposed to be less than 0.02, and we are at 0.02 right now. So the story is we've already mass produced these brackets. Let's just say there's about 1,000 of them out there. What can we do to fix this bracket? And the weight for this bracket is going to be important for whatever reason. It could be for shipping cost, or even a reduction in the size of anything that we introduce can reduce the cost. So we're going to introduce a gusset to reduce that deflection from the bracket. And it's highlighted here in orange. And the goal is to keep the bracket size, this gusset, to try to reduce the size of it, because that will reduce the cost. At the same time, we don't want to impact the weight of this bracket. So we're going to be using tools to set parameters on this bracket itself. So we can do a study on it, design experiments. Okay, so let's get into it. I'm going to start with a static structural study, and we're going to be setting up these parameters. In my last AVA session, I did cover how to import parameters from Inventor. For this one, I'm going to do it directly in SpaceClaim. I'm going to import the bracket, and we're going to set this up. And please feel free to ask questions. This is an interactive AVA session. So over here, I've introduced this gusset. And we want to assume that it's already fused and welded to the part. So I'm going to combine it together. And we're going to introduce some radiuses in here. So what I'm doing right now is I'm double clicking on these edges, and it's going to select the most adjacent edges that they can find. Space Claim is pretty good with that. It tries to do like a lot of different features to do smart selections. So here I'm gonna double click here again. I'm gonna double click once more. It's gonna try to find the most adjacent edges. So I can do a feature like so. I'll pull this. Let's say for now I want to put that to 3. Okay. So Space Claim's not like your native CADs where you have dimensions and you set parameters with those dimensions. It works with it doesn't have a design tree. It's just a literal 3D modeler where you manipulate things. So I'm going to set parameters using the features in Space Claim. So if I had this pull feature here and I'm pulling this, it's going to change it directly here. So the first thing I want to do is set up an offset feature. And what that means is it's going to set a reference plane right in between. And I want to offset it off of that in this middle section. So I'm going to use, that's what the offset's going to be used for. See if the offset's going to be displayed. Okay, good. Now I'm going to do that pull feature again that I showed a little earlier, except this time I'm going to tell it to use that offset that I just set. And I want to set it to the center. And when I click on this yellow arrow, I'll get the ability to set a ruler. That's very similar to your native CAD where you're setting dimensions. And right now it's set to the right face. And I'm going to make that ruler on the left side of this face. And that's going to give me, it's currently 5 millimeters thick. And I'm going to parameterize this. So that should give me the ability to offset this. So if I type in 20, it's going to offset it from the middle. And it's been parameterized. Set this to 4. Oops. Set this to 4. Okay. It's always good practice to name your parameters, or else it's going to be stuck as group 1. So when later on, when you're observing your parameters in your parameter set in Ansys, it's going to say group 1. It's going to be confusing. So it's good practice to give them names. This one's going to be thickness. And the next parameter set I'm going to make is going to be the height. So it's going to be this feature and its vertical dimension from this small point I made. I made this point from a sketch earlier. So you can set your parameters to a datum point. You can make your own datum points. And I'm using this point as a datum right now. So when I click on this radius here, I could use the move feature in Space Claim. And when I observe it from the side, it doesn't look like it's going to move in the right direction. So I'm going to make sure it does by using the move in a direction feature. So after clicking this arrow, I can select which direction I want it to move in, or rather it's going to turn the axis aligned to this one, this line I just clicked. And now I can hit this red arrow and move this feature up and down in this direction. But I don't want to do that because I'm going to parameterize it. I'm going to set a ruler. I'm going to click on that point I made, and I'm going to parameterize that by clicking the letter P here. So now I've set my 2 parameters. And like I said earlier, it's good practice for us to name these parameters. So I can manipulate this, and I'm going to apply it a height of 70. As I said before. Okay. So let's close this down. Let's run our initial simulation. So you can see, since I set those parameters, when you're looking at the workbench GUI, you can see I have this new box down here and it's parameter set. So we'll jump back into there after we run our simulation. So we're going to fix these points, or rather these surfaces, not points. We're going to apply a frictionless support in the back of this bracket as it sits against a wall. And we're going to apply a force. 2,000 pounds. It's currently not set in the right direction. It's going up normal to the surface. So we're going to change that direction. All right, click apply. And we are interested in the stress. We're interested in the total deformation for deflection. And we are also interested in our factor of safety. So here's the next step that's important, because earlier we set inputs as our parameters. Those are going to be features or values that we change. Now I'm going to be setting parameters from the outputs. So it's like cause and effect from your inputs. And I'm going to parameterize the mass. So I'm going to select geometry, and you can see where it says mass here. There's going to be a little box here. That's not a checkbox. That's actually your parameterization box. And when I click here, it's going to parameterize mass. And I could do the same for stress, deflection, and my factor of safety. And I know this is a coarse mesh, but it's good enough for us just to review the features of DesignXplorer. We can see the deflection is 0.007 approximately. And that's already a big improvement from 0.02. Let's just assume that this is acceptable. And I could call this design complete and done at this point. But what if I work somewhere where we mass produce various different parts? And what if I wanted to do a study to minimize the size of this bracket? I can do that using DesignXplorer. And it doesn't take me hours to do that. I don't have to keep continuously change the model over and over and over again. I can use DesignXplorer to run a design of experiments and see response surfaces for me to understand which is the most optimal bracket based off of my own criteria. And for today's criteria, it's going to be to minimize the mass, minimize the deflection. We want to have have the highest factor of safety as well. And you can see in these parameter sets, I can actually change my inputs here. If I wanted different inputs, I don't know why that one's still 35. I could type in different thicknesses and heights and have it solve in the simulation itself. And it will give me my outputs for me to understand all that. But rather than do that, we're going to use DesignXplorer to do that for us. And that's as simple as dragging and dropping DesignXplorer tools into the workbench fields or the open cell work area. So I am using response surface optimization for this demonstration. The first thing we're going to do is, oh, you know what? Let me set this up. I'm going to have this simulation run parallel so we can use more cores. So let's start by opening up the design of experiments. You know what? That bound is really wrong. It should have been 4. So here we are, and we're going to set up our design experiments. That's going to be a table of various different design points for those inputs and outputs. Let me see here. Not FEA related, but can DesignXplorer be used for CFD analysis in Fluent? Snigdha, did you want to answer that one? I know it can, but I believe that you'd give the best answer.
Yes. In fact, we will be doing a CFD AVA soon that takes use of the DesignXplorer parametric analysis to generate something similar. And, I think that AVA might be of use for the participant.
Awesome.
Yep.
Yes. Yes, so DesignXplorer works on both tools. That's awesome.
Yeah, DesignXplorer, from what I know, is basically something that you have available to you within Workbench itself. So whether you do a fluid analysis or a structure analysis or a multi-physics analysis, you could use that to set up your parameters and get the response that you need.
Okay. Thanks, Snigdha.
Sure.
So there are going to be different types. This is using a statistical approach to solve our design sets or our design points here. And I can go into describing all of these settings, but I don't think that's going to be exciting for this AVA session. But there's great material, and this is a great segue for me to talk about the Ansys Learning Hub. There's a lot of great material on the Ansys Learning Hub that covers DesignXplorer and all of these specific details of these settings. And if you are interested in getting access to the Ansys Learning Hub, please give us a, you could contact us through our email or phone number. For this one, I'm going to be using face-centered and enhanced. And for thickness, I'm going to be using my boundary points. So let's say the materials available to me are going to be 4 millimeters thick to 10 millimeters thick. And I can actually set, if I wanted to, manufacturing values. So let's say if they were in 6, 8, and 10. But for this simulation, I'm going to be just using any. For the height, I'm going to limit it from 40 to 70. I hope this doesn't get messed up because for some reason it was set to 35 millimeters earlier. And in doing so, I'm going to hit the preview button here. And it's going to select various design points that DesignXplorer believes it needs to solve for it to start predicting all the responses, the mechanical responses of the simulation that we set up. And normally I'd hit update and it would solve for about 15 to 20 minutes. And that's not something I want to do in this AVA session. So assume that I hit update and all of these points were solved here. That's going to be 17 different design points will be solved. I'm going to close this down because I already actually have this solved for us to save us all time. And we can see all 17 design points solved here. And that's varied different types of thickness sizes from when we set it to 4 to 10. And it's different heights from 40 to 70. And to us, it almost looks like there's no pattern to this. It almost looks like a bunch of randomness. And that's what it needs. It needs a bunch of different random points for it to solve. So we can use a statistical approach to estimate the simulation results later. And we'll cover that. But right now, I just want to show this feature over here. It's going to be the parameters parallel chart. Let me see if I can reset this. Sorry, it's so sensitive. You gotta just get right over this line perfectly. So what do all these lines mean to me? Well, they correlate with this chart up here. If I highlight one of these lines, it'll tell me that this is the design point number 15. And it's gonna correlate with each, as I go from left to right on this chart, it's gonna be the parameters we set. So that's gonna be thickness, height, geometry mass, the stress, deflection, and the factor of safety. And I can actually use this tool to filter out results I'm not interested in. What if I'm interested in everything that's 4 millimeters and below? So there's a little arrow I can click over here and drag and drop it up and down. I'm gonna drag it down here to about 6. There's no results at 6 and above. So that's just gonna highlight all of the 4 millimeter thickness results. And what if I wanted to say, okay, I want the height to be, let's see what is set up to. I want the height to be above, what's that probably, it's not giving me a number right now. But what if I wanted the height to be above, below 70, but above 60 right now? And that's going to show me the correlation here and the results of how of its mass, stress, and deflection, and the factor of safety, which is not 1. So that's not good. We want its factor of safety 1. So I'm going to redo this, but make sure I have a factor of safety of 1. So everything over here is pass. The factor of safety. So from here, I could guess that this design point here, it's going to actually give me the highest factor of safety, and it actually is the thinnest and a 40 millimeter height approximately. And this is design point number 11. So just from this tool alone, I can already select this design point if I wanted to. I could set it and I could solve it inside of my simulation. But I want to explore a little bit more with the other tools of DesignXplorer. So the next step I'm going to go to is the response surface. And from here, I would have clicked update and it would have updated it in about 2 minutes. So I've already ran this though. So from here, it's going to share with us the statistical approaches that it's going to use to solve this. And we check the quality of these statistics. There's a lot of different information that we can look through on this table. And once again, each one of these has a purpose. And that is detailed very well in the Ansys help documentation. Or again, if you guys are interested in the Ansys Learning Hub, please contact us. And if you're a customer of ours for Ansys, contact your sales rep. We can have a discussion on that. But I'm going to show you something that's much easier to understand for this demonstration. And it's going to be called the goodness of fit, where it takes the statistical approach that it's solved for those design points, and it's going to compare them to the actual solved design points of Ansys. And the better it fits along this linear line, the better your data is. So you can see a good example of good data almost fitting perfectly on this line, and a bunch of bad data. So if you have a poor quality like this chart over here, I would check how the parameters were set, because there can be a feature that might be interrupting with another feature in the way you set up your parameter, and it's not giving you good data. And it could also be the design points that were selected previously that it's not giving you good data. So let's check our goodness of fit for this simulation. And it roughly follows the line. It's not the best. We could probably do better, but it's going to be good enough for us to go over these features here. Now, the next feature I'm going to go to is the min-max search. And when I look at the min-max search, it's going to give me all the minimum values that it can study for all the inputs and the outputs. So if I'm interested in the minimum mass, it found it at 4 millimeters thickness and 40 millimeters height. That's the minimum mass. It also found that the maximum mass is at 10 millimeters thick and 70 millimeters height. And that makes sense to me because the gusset is larger. It's adding more mass. And you will notice that all of these numbers are blue in color. And the reason why is because this is based off of the statistical approach I was talking about with DesignXplorer. This means that it's a rough estimate. These are actually not verified in the simulation yet, but we can do that, and I'll get to that in a few minutes. And the next part I like with this statistical approach is it can predict other sets of data that we're interested in very quickly. And again, this is an estimate, but if I were to type in, I'm interested in 7 millimeters, and what if it was 65 millimeter height? It's going to give me really quick data points right here in estimates. I can just go in there and type 4.5, and I can type 63.5, and it's going to give me a rough estimate for this data here, for these data sets and the factor of safeties. So from using the response surface, it gives you the capability of getting a quick estimate and understanding of how my inputs affect my outputs. And I like this feature. It's pretty cool. And the next feature that we're going to cover in the response surface is the ability to graphically see this data. What if I wanted to see how the thickness affects the mass? Now, it's quite obvious. The thicker the part, mass is going to go up. But what if I wanted to see that in 3D? And this is going to be set for the Y. The x-axis is thickness, the y-axis is height, and we're checking mass. And in this 3D graph, we can see that mass is going up for height. As you increase height, mass continues to go up. As you increase thickness, mass continues to go up. Now the next feature I like is the local sensitivities. Now I can compare the inputs and see how they really do affect my analysis. And this is similar to my last demonstration where we went over the correlations. Taking a look at this, we can see that the thickness actually affects the mass more than the height. And we could tell by highlighting these design points. So I'm gonna highlight design point number where it's 4 millimeters thick here, and it's 8 millimeters thick here. And we could take a look at the mass and how it changes compared to when we double up. So from here, we're doubling the thickness, and we can see how the mass is affected. Now we're going to compare that to when we choose 4 millimeters thick with a 70 millimeter height. And we're going to go 4 millimeters thick with a 40 millimeters height. We can see that the thickness, by changing the thickness, it actually affects the mass more. That's what these bars mean. And by changing the thickness, it's affecting the stress. It's reducing the stress. That's in this next bar chart over here. So I'm going to go back to, let's observe the thickness at 4 millimeters and 8 millimeters thick. And let's take a look at those stress results. Wow, it reduces the stress quite a bit by just doubling the thickness. But the same can't be said with the height. So I'm going to go back to highlighting these points over here. 70 millimeters height with 4 millimeter thickness and 40. And we can take a look at those stress results. And you can see that by doubling the height, it's not really reducing the stress that much. Can you export the response surface values to, say, an Excel sheet? Yeah, you can actually right click and copy this. Sorry, I'm answering one of the questions. You should be able to copy and paste that into Excel. And once again, these are, these are estimated values, and that's why they're highlighted in blue. But yeah, feel free to select this chart, this table, and copy it and export it into Excel if you'd like. Okay, now here's the fun part: using the optimization tool. From here, I can set criteria that I want. And I had already preset geometry mass. I wanted to find the a design point where it minimizes mass, it minimizes deformation and deflection, it maximizes my factor of safety, and it minimizes the thickness and the height. And I simply set that within this table. So you can set your parameter first in here. You can select the value, and then you can set it to minimize, maximize, or even seek a target. But I've already set these values because I know that what I want to minimize and what I want to maximize. And by clicking update, it will solve for about 3 to 4 minutes using the statistics that it collected. And it will give us the candidates that it finds with all of these values that we set. And you can see candidates 1, 2, and 3. What's important to me is the factor of safety, as well as the weight and the deflection. Let's assume we wanted to go with design point number 1. I can right click design point number 1, and you can see these numbers are still blue. That means it's an estimate. I can right click this design point number 1, and I could hit validate. Let me go over on highlight number 2, and I could verify this design point. And what it's going to do, it's going to take these numbers, the inputs, and it's going to insert it into Ansys Mechanical, and it's going to solve inside of our simulation rather than using this statistical approach. Sorry, it's like a tongue twister. And I can actually import that as a design point. So I can insert this as a design point, go to my parameter set. I could see it over here. And it's solved using the simulation. And if I right click this, I can set it as current. And when I set it as current, oh, you know what? There's a step I skipped. Let me go back to that. If you click over here and you retain the data, then you can, when you save it, it's going to save those all as simulations that are completed. So when you set them as current, it'll do something. It'll do this. And here in our simulation, we can see that it has selected that thickness from the design experiments and that height. And it's giving us a 1.2 factor of safety, which is a bit better than what the statistics showed because it had a 1.19 factor of safety. From here, if I wanted, I can also, I have the ability to set this to a coarser mesh and to solve this as well. So rather than setting up various different geometries in my CAD or even doing it in Space Claim and doing different studies and duplicating different schematic studies and solving this over and over and over again, I just used DesignXplorer. It took me approximately 30 minutes and I set a lower and upper bound of ranges that I wanted it to study in. And I obtained these results. And I'm confident that if I were to create a gusset about this size and it was welded to this bracket, that we would have accomplished our goal of reducing that deflection here and not sacrifice a factor of safety below 1. Let's see here. We have some more questions. Can you set the objective to be constrained by a value such as minimize mass, but make sure it doesn't fall below X kilograms? Yes, you can. So the question is, someone asked a question about those optimization metrics that we set. Can we set exact values? Yes, we can. Can we set upper and lower boundaries on them? And that's, yes, you can manipulate that type. You could do lower, upper, or equal. So that concludes this AVA session. Thank you very much, everybody.
Thank you.